Hello guys, I am Bhavik Joshi. Today we will talk about the CFD simulation of Formula 1 car. So let's get started. So here I have imported the model of a Mercedes AMG Formula 1 car. In this video we will learn how to interpret the results, the pre-processing and the post-processing in Solidworks by Flow EFD solver. Okay, so let's get started. First we have imported our model, which is a solid body. Then we have to save the model before getting into the CFD simulation. So we have saved the model. Then go to the SolidWorks add-in. If your SolidWorks flow simulation is not active, so you can perform the analysis. So you have to active the SolidWorks flow simulation first. Then go to the flow simulation panel, okay, in command manager. Here you can find a lot of options are there, okay. So for this kind of analysis, we will start with the any kind of simulation. You have to start with the wizard, where you can set up your environment, and a lot of boundary conditions are there, okay. So we will start with the wizard. In the wizard you can name your project, okay. I am naming it Formula 1 CFD. Then you can choose your configuration if there is any you have created, customized, okay. And also the name you can change. So we will move forward. Next, here you can select your unit system, okay. Mass in kgs, okay. Temperature is Celsius. I will take Celsius, okay. Next here there are two types of analysis. One is internal, and second one is external. So for this kind of analysis, aerodynamic analysis, you have to check the external analysis, okay. So here untick two option: extrude cavity without flow condition, also we have not required, and extrude internal space also we have not required. So this and fluid flow, okay. Conduction is not there because we are not doing a heat transfer analysis. Next one is a time dependent, means transient analysis, okay. Then gravity, if you have, if you want to turn on rotation part of it, like turbocharger analysis. If you can create your rotating region, if your wheels are rotating, you can check the rotation region. Also I will show another option how to move the surface of the tire in the simulation. Free surface also we have not required right now, so we'll move forward. Next, here you can select the gases, like I am doing air, okay. Here you can select the flow type, laminar and turbulent, okay. High Mach number flow, humidity, okay. Next, here is the wall condition. We will skip to the part. Here you can select the turbulence parameter as well. In other software there are a lot of option of turbulence model, select k omega, k epsilon, but here we can select the customized turbulence parameters like turbulence intensity and turbulence length. We will not change right now. So here velocity parameters, if I have to do analysis at, so my car is in x direction, okay, forward x direction, so my flow will be in a minus x direction. So I have to do like 100 minus 100 kph, okay. So I have to put down minus 100 kilometer per hour, okay, minus 27.77, okay, done. Next you can select the pressure, select the temperature, which is a environmental condition, okay. Then we will move forward. Next, finish. So here you can see my computational domain is already set up automatically. So here you can check like the rear part of it have to be 3 times larger than the length. So approximately this, and I'm setting up like, so you can create a one surface as a ground, okay. Then okay, then in the front view I will decrease the area, for less computational time for now. Okay, you can enlarge it as you want. Okay, for the larger accuracy, great accuracy. Okay, so here I have set up the computation domain in which area the flow will be affecting the car. Okay, next, if you want to rotate the wheels, so here you can check the wall condition, a real wall or ideal wall. Okay, wall motion, check the wall motion, and then select the surfaces. Then you can give the angular velocity and velocity to the whichever surface you have selected. Okay, so we are not doing for the, because it consumes a lot of time for computing, that's why. Here you can select the goals, like if you want to calculate the drag force, your down force. Okay, so here you can check. Okay, the velocity, the turbulence parameters, the normal forces. Okay, in a x direction will be a drag force, the y direction will be the down force. So this kind of forces you can check here. Okay, the overall normal force. Okay, here I will tick. Then also you can make your own equations by putting it here, equation goals. So you can directly gain the value of your coefficient of drag. Okay, here is a global mesh, you can customize your mesh. So my basic mesh size is right here, which was a default size of the computational domain, so I will keep it the default. You can create your custom local mesh here, but I will not do that because it consumes a lot of time. Okay, so we are ready with the pre-processing. Now we have to run the results. So what you can do, simply run, and here you can tick the solve and run. So you can see that your analysis is running. There is no warning right here. The number of cores, how much time it will consume, the iterations it is doing. Okay, so my time will be, calculation time left. Okay, okay, the solver is finished, right? You can close this panel, and here you can see the results are here. Now you are in the post processing part right now. You can hide the computational domain for now. Okay, now if you want to see the cut plots of velocity, here I am adding the cut plot in this plane. Okay, now click here. Okay, so here you can see the velocity plot, the pressure plot, and here you can change the parameters, the velocity, how it is affecting. Okay, here you can select the Mach number as well, the pressure, the temperature, anything you want to interpret. So now you want to plot the trajectories, the 3D trajectories, the streamlines. Okay, so you have to go to the part, the flow trajectories. Into the flow trajectories you have to select the plane. I am selecting the right plane because it will flow the perpendicular to the plane, so I will keep it at this. And how much points you want to add from uh, from where it will begin. So I will create 50 points. The types of streamline: pipes, lines with arrows. So I will check the arrows flat. It will look good, I think. The velocity, okay, now good. It's very small, so I will change the pipes. Okay, so here you can see your trajectories are good, like interpreting. Okay, now here you can try a lot of options for the better visual graphical interpretation. Okay, but I am skipping that part. I am showing the how you can like fade. First I have to delete it. I will hide and then insert. Now you have to check whether my flow is going into a particular part or not, how it is flowing, the direction of flow, like a front wing to the brake duct part. Okay, how much flow it is taking, and that affects the cooling of the Formula 1 car. These are the brake ducts. So basically I will start selecting the parts where my where I want to interpret the flow trajectories. So I will create the 50. Okay, okay. So here you can see from this these airfoils are diverging the flow, and this flow is directly going into the brake duct part. Okay, so that's how you can select the particular parts for the flow trajectories. So I will select the rear spoiler. Okay, the DRS, the airfoil, this airfoil. Okay, and I will select the 100. Okay, so you can see that flow, the starting points of this flow will directly touch to the rear part of it. So here you can see how the turbulence is getting generated. Okay, now so you can play the animation. So I will select the difference surfaces. This surfaces you can select edge also, edge points, whatever you want. Here you can see how my flow is directing from the front wing to the rear tires. Okay, so here how you can do a basic simulation, a basic CFD simulation before moving on to the advanced part in Fluent Star CCM Plus. Okay, so you have to know a basic first. So here you can gain the confidence as well. Okay, next, what about the forces which we have done in pre-processing? So for that portion of we can select the goal plot in a post-processing part, select the insert and select all. Okay, so whenever you will show, it will show you the graph how it is changing according to the iterations. Okay, and also in the summary there are the values. Okay, So that's how you can find the drag force, the down force, coefficient of drag, frontal area. You have to calculate the frontal area as well. Okay. So also you can generate the report from here, create report. Okay. So you can select the template, the pictures, okay, then the IDs, the input data, the results. Okay. Also you can select the, so if I do a section in the, yes, now, okay, I have done the section part and I will change the scene. Now I will insert a flow trajectories, clear. Okay, so I will select the brake duct part, this part. I'm checking my flow is, how my flow is diverting to this part from the front wings. Okay, so I will select the 100. The larger number you will input, the larger time it will take to calculate. Okay. So here you can see the flow. So that's all for today. For the advanced part, like a moving tire simulation, the equation part of it, the surface plots, the transient simulation, we will do into the next future videos. So please like and share, and thank you for being here to the end. Hello guys, welcome back to my channel with another episode of Formula 1 CFD car. Welcome back to the DP design. So in the previous video we have done the basic simulation of Formula 1 CFD car. A lot of guys goals. What if tire is moving? What if ground is moving? Okay, so that kind of stuff we will cover in this video, and maybe in the next video, in the episode 3, we will do a dynamic simulation, like tires are rotating, ground is moving. Also we can check the DRS if possible, okay, according to the surface condition. So let's get started. We will cover in this video the basic equation goal. Okay, so how to create an equation for the coefficient of drag and how to interpret the results according to that. So let's get started. Hope you will enjoy the video. Okay, let's do it then. Okay, in the previous video we have done the like in the general condition we have done the external flow simulation. The basic recap I am doing. In the fluids we have selected the air, flow type, laminar and turbulent, both we will do, and also initial and ambient condition. Here I am taking the velocity in x direction, okay, in this direction. Okay, so it is in a plus direction, so I will do it minus 100 meter per second. Okay, yo. Now, so the arrow is denoting the velocity, the direction of the velocity. Okay, I'm apply. Okay, next one we will move on to the boundary condition. In the boundary condition there are two types of walls are there. Okay, the first one is for the intake parameters, like inlet, what is the inlet mass flow. So these parameters are not related to this kind of simulation. Then the environmental pressure, the static pressure you can give. Now we will talk about the real wall and ideal wall. Real wall is basically what, no sleep condition in the other software, you will know, where real fluids are sticking to the wall, okay, and also creating the boundary layer at the different locations. So, so I'm basically creating the, so if this is your flow and this is your ground, this is your flow, so at particular time is equal to u is equal to 0, u is equal to y. So here it will, so this can be also known as free stream velocity or oncoming flow, okay. Now it will create a boundary layer like this. So the fluids are sticking to the wall, and in the ideal wall there will be no friction. So the ideal wall is basically used for the symmetrical objects. If you want to make a symmetrical objects, okay, in the pipes also you can do where it is no friction. So in the no friction condition you can take a ideal wall. So I am taking the real wall. Basically ideal wall creates a, like less takes a less computational time, and real walls are uh, basically a complex type, and it will consume a lot of your CPU time. Okay, so coming back to this, we will discuss this in later, how to give a velocity and how to give a rotating regions. Okay, next one we will define the goals first. In the goals you can select a point goals, you can create a global goal, surface, particular surface, volume goal, and the equation goals. So in the global goals we will select the, there are two types of forces are there. First one is a normal and second one is a normal force, okay. So what is the difference between them? So this force in the x direction, this will create, okay, this will include the all various types of forces which are acting in the x direction. You can take this force if you want to calculate the skin friction drag, okay. The skin friction drag will also be included in this type of forces, and the normal force we will only calculate the perpendicular force according to the in the reference of the x axis, okay. So this is the difference, the major difference between the normal force and the force. So we will take a normal force in the x direction, and the normal force in the y direction I am taking for the down force, calculation of down force. And next one is a coefficient of drag. Now how to create a equation goal? So here you can build the, here I am selecting the any point, okay. So you can check out the where you want to measure the force at particular point, okay. So next one is the equation goals. In the equation goals, if I'm naming it a coefficient of drag, okay, then you can put out the 2 into drag force according to this formula, okay. So according to this formula, 2 into drag force, my drag force will be in Newton, the area into area will be into meter square, density kg per meter cube, and velocity is equal to mass, meter per second, okay. So this is the basic formula for the coefficient of drag. So how to plot this formula into the equation? So I am taking 2 into a drag force. What will be my drag force in the x direction? This one. So here gg normal force, okay, in the x direction. Now divide by, I am taking into the this. Now my rho, like density, area, and the velocity square. So here you can put down whatever value you have calculated, okay. So here I have done the one equation, 2 into normal drag force upon 1.27, 1.37. 1.27 is basically your density of air, 1.37 meters square is a frontal area of the car, and 100 square, that is my velocity. Okay, so here I am closing it. Here you can check the, and here you can select the unit coefficient of drag having a no units. Okay, so okay, I will click the OK. Next we will move on to the meshing part. So Solidworks is not basically a very advanced in meshing part, but here this will separate. This is my basic meshing have been done by the software itself. So I'm adding this mesh and adding the local mesh. Okay, insert a local mesh, then you can select the part. Okay, select the surfaces where you want to refine the cells. Okay, the level of refining refining cells. Okay, so there are lots of parameters are there, the advanced refinement. Okay, so here you can change the parameters according to your requirement. So I am not doing any changes in that because it will create a highest computational time for me. It will consume a lot of time, so I am keeping it unchanged. Now to calculate these three portions, okay, I will run the simulation. If you want to take the previous result, I don't want to take the previous result. Okay, I will run, and here you can see this is preparing the model for meshing. Now here the value of my coefficient of drag is calculating. Okay, the normal force in y direction. The minus sign is basically giving the direction. That doesn't matter at all. Okay, the list of goals have been calculated, so I am closing it. Here you can check your CD value. Okay, in this part. So okay, so here is my CD graph. You can check out this. The solver is finished, so we will go back to the post processing. Here you can check the mesh, how your mesh have generated. Okay, the cut plots. Now we will move on to the goal plots. If you want to check the CD value, the force value, okay, so I will click the insert and going on to the all or only CD. CPU time, iteration or travels, you can take the reference in the graph. I will click on the show. Here is my value, a 0.48, a coefficient of drag value. Okay. So this is how you calculate the coefficient of drag value, and also you can edit the definition, and also forces value you can also check. These are my force value have been calculated in this computational term. Okay, so that's how you calculate the equation goals. That how you make the in the equation, like you can customize your expression. Yeah, this is basically I have done the most usable parameters in the pipe flow. Like if you want to calculate the pressure drop in the venturi, so you can get the expression and make an equation, a customized equation according to your requirement. Okay, so that's how you do it, and we will move on to the next post processing part, how you interpret the result and how the fluid flow is flowing. So in the previous video we have done the basic post processing. Here you can check the dynamic trajectories. Okay, in the dynamic trajectory we have two options, the arrows are there and the spheres are there. So in the arrows we will decrease the size, the distance between them, like I'm creating 20, and here I'm changing the parameter to velocity plot. Okay, here you can crop the region. It will basically create a computational domain. The constraints you can check. Okay, now I will select the front wing part for the fluid flow. Okay, you can check the mesh based generation. I will create the 50. So here you can see how the fluid flow is flowing, right? And also you can play, you can save it to the animation as well if you want to animate. Here you can change the scene. You can see that. Okay. Now there will be a customizable, like I'm not using it very oftenly, but still you can select the mesh based generator or point based generator, rectangle, sphere, where you want to create the, from where it will start. You can decide that. So I am taking the line. Okay, these are my lines. So I will create the 50. I am creating the 100. I will keep it 100. Okay. Next one. Okay. So see. You can see that as I'm editing this, so I'm creating a rectangle. So press space, moving into this part and moving to this part, and I will create a 200 for better visualization of the fluid flow. So that's how you process the results. And in the advanced, like you can create your customized cut plots, the ISO lines only. For the ISO lines, the velocity, I will turn off the contour, make it transparent, and the velocity, display values, so I will click it off. So here you can see the major changes in velocity area. You can see that in the ISO lines the major changes are there. Okay, so here you can select the we'll keep it as 0. This is the offset from the plane only. You can change that. So I am taking the 255 iteration. Yeah, here you have the better visualization where are the stagnant points, where the stagnancy effect can take place. Okay, where the velocity is changing. So and also you can change to the vectors, the streamlines, this will not give you a like detailed idea. I'm not using it the streamlines, but vectors, yes. The ISO lines is very helpful tool for the check the parameters. So here you can see that the pressure values. So that's all for today, and we'll meet in the next video for how to give a rotating tire regions. Okay, so thank you for being here and thank you for support. uh, Jai Hind.